pretty much every piece of modern electronics, from the phone in your pocket to a satellite orbiting the Earth, it's all built on the transistor. But what's the fundamental rule, the actual source code that makes it work? Well, today we're going to crack it open. If you've ever tinkered around with a transistor and a multimeter, you've probably noticed it kind of acts just like two diodes connected back to back. So that leads to a pretty obvious question. Why can't you just grab two regular diodes, wire them up, and call it a day? I mean, it seems like it should work, right? But nope, it absolutely will not work. So what's the deal? What are we missing here? Well, the reason it fails is because that simple two-diode picture is leaving out the most important part. See, real transistors have this hidden link, a sort of ghost connection that exists between those two junctions. And that connection, that's everything. It's the secret sauce that lets a transistor amplify a signal or act like a switch. And this ghost connection isn't just some vague, hand-wavy idea. Oh no. It is described perfectly by a mathematical model, a model we can really think of as the transistor's actual source code. It's called the Ebers-Moll Model, and you can think of it as the complete, unabridged instruction manual for a bipolar junction transistor, or a BJT. It lays it all out. A BJT is not just two diodes, it's two diodes plus that ghost connection, which the model describes as two dependent current sources. Now, what does that fancy term mean? It's simple, really. It just means the current flowing in one part of the transistor is grabbing the controls for the current in another part. It's this link that lets us predict exactly what a transistor is going to do. Okay, I know, dependent current sources still sounds a bit academic. So let's ditch the math for a second and use a really great analogy to make this crystal clear. Let's imagine the electrons zipping through a transistor are just like cars driving down a highway. All right, so here's how our highway works. First up, the base emitter junction. That's our toll booth. To get on the highway, every electron, every car, has to pay a tiny little toll of about 0.7 volts. But here's where the magic happens. The base region itself is physically super thin. So once those electrons pay up, something like 99% of them don't even bother stopping at the base exit. Nope. They get totally swept up by the big voltage at the collector and just zoom right past down the main highway. That is our ghost connection in action. And the base collector junction? For now, just think of it as an exit ramp that's closed to any incoming traffic. And that right there is the key to the whole thing. Okay, but here's where it gets really cool. This model isn't just a one-trick pony. See, our highway can have different traffic conditions, right? Open roads, traffic jams, road closures. And depending on how we're using the transistor, the model actually morphs to describe each one of those states perfectly. And this table just lays it all out beautifully. So first, you've got cutoff. Think of this as road closed. Both diodes are off, so nothing is flowing. In the real world, that's a switch that's turned off. Your fan is just sitting there not spinning. Then you've got the active region. This is our open road. The toll booth's open, but the exit is closed. This is the sweet spot for an amplifier, right? Like in your stereo? Next up, saturation. This is a total traffic jam. Now both diodes are on and it's just a flood of current. This is a switch that's fully on, like your fan spinning at top speed. And yeah, there's reverse mode, which is basically like driving backwards on the highway. You can do it, but you probably should. So let's zoom in a bit. Let's look at that active region first, the one we use for amplifiers. When we're on this nice open road, that whole complicated Ebers-Moll model, well, it simplifies itself down into something way easier to handle. So, in the active region, what's happening? Our toll booth is open for business, but that exit ramp is still closed off. The entire complex model just boils down to this one beautiful idea. You have a simple little diode that's now in control of a huge, powerful current source. I love this analogy. It's like a tiny water tap controlling a massive pressure washer. A teeny tiny turn of that tap, that's your base current, unleashes this gigantic, powerful, but perfectly controlled stream of water. And that's your collector current. And that, my friends, is amplification. Okay, that's great for amplifiers. But what if we just want a simple switch, just on or off? Well, for that, we need to completely change the traffic conditions. We're going to slam the transistor into saturation. The highway becomes a total gridlock, and believe it or not, the model simplifies. Again. So in saturation, what we're doing is just flooding the base with so much current that the transistor literally can't handle it. The collector current maxes out, and because of that, the collector voltage just plummets.
It drops so low that, get this, our exit ramp, the base collector diode, actually turns on and starts letting traffic through. It's like the exit ramp itself just gets flooded. The whole beautiful amplification system is totally overwhelmed and the transistor just gives up. It acts like a simple closed switch with a teeny tiny voltage drop, maybe 0.2 volts across it.
Let's make this super real with a classic hobby project, right? Using an Arduino to turn a 12-volt fan on and off. So, step 1, the Arduino pin goes high. That sends a little bit of current into the base, which is more than enough to shove the transistor deep into saturation. Bam! It acts like a closed switch, the fan gets its connection to ground, and it turns on at full blast. Step 2, the Arduino pin goes low. The base current gets cut off. The transistor immediately snaps into cutoff mode. The switch is now open, the fan loses its connection, and it stops spinning. See? It's that simple. We're just flipping between traffic jam and road closed. All right, so we've gone through all this. The diodes, the highway, the traffic jams. What's the big idea here? What's the main takeaway? When you zoom out, how should we really think about this Ebers-Moll model?
Honestly, the absolute best way to frame this is to think of the Ebers-Moll model as the Ohm's law for transistors. Seriously. Just like Ohm's law is the unbreakable fundamental rule for resistors, the Ebers-Moll model is that core foundational principle that dictates everything a BGT does. Everything, from boosting the signal in your headphones to switching on a massive motor. And that kind of leaves us with a pretty cool thought to chew on, doesn't it? If the humble transistor has a deep fundamental source code like this, what other essential rules, what other elegant models are just hiding there right under our noses, running all the other